In this video, we're going to learn a bit about analyzing problems with work and energy. So, for starters, I want to talk about 4 properties that should be true about the problems that we're analyzing using work and energy concepts. First of all, we should have some sort of system, which consists of 2 or more objects. We should be able to clearly define our system. Second, the force that acts between a particle-like object in the system, the force should act between a particle-like object in the system and the rest of the system. Most of our objects are particle-like. In other words, they travel as a whole object and they're fairly uniform in shape. Third, when the system configuration changes, the force should do work on the particle-like object, transferring energy between the kinetic energy of the object and some other energy of the system. And finally, when the configuration change is reversed, so when it goes back to the way it is, the force should reverse the energy transfer, doing work W2 in the process. Let's talk a little bit more about that idea of the system configuration change in terms of something that we like to call conservative forces. So here I have 2 paths traveling between points A and B. Path 1, you can see, takes one route to get between A and B, and path 2 just takes a slightly different route. If we have a conservative force, then the net work that's done about any closed path is 0. In other words, if I go from point A to point B, and then I go back to point A, the total work that's done would be 0. Another way of stating this would be work 1, just as we defined it in previously, would be equal to negative work 2. So when I would add those 2 together, I'd get 0. Some examples of a conservative force would be the gravitational force, or tension is often a conservative force. The spring force even is a conservative force. An excellent example of a non-conservative force would be the force of friction. The reason we care so much about conservative and non-conservative forces stems from the idea of conservation of mechanical energy. Mechanical energy is considered to be the combination of kinetic and potential energies. Now, we know that work, really the net work, is equal to the change in kinetic energy. We also know that net work is equal to the negative change in potential energy. So, therefore, the change in kinetic energy is equal to the negative change in potential energy. Or, another way of writing this is that the initial mechanical energy is equal to the final mechanical energy. Or saying that K initial plus U initial equals K final plus U final. Now, the reason we mentioned conservative and non-conservative forces is that mechanical energy is only conserved when all of the forces acting on your object are conservative forces. If for some reason you have a non-conservative force, then mechanical energy is not conserved, and we'll deal more with that later in class.